with this knowledge, we can do very fancy things. So I want to talk about randomness today. We want to be very random. And remember, at the start of class, like the very first day, we talked about the word randomness, and it was like, don't think of, in this class, don't think of the word randomness as like haphazard. We're doing things carelessly. Randomness for us is just like we're flipping coins and we're using that to do statistics and do wonderful mathematical things through randomness. So randomness is a good thing for us. All right. So this is chapter 9. A lot of fun concepts I'm required to talk to you about, but please start reading that now. It just gets better. So I guess the very first thing I want to talk about is a piece of the NumPy library, numpy.random. So you can remember that NumPy is a library that works on sequences, those arrays that we've been talking about, and it's got a bunch of functions in a bunch of different places. It's got np.random stuff. So let's go look at that. All right. Surely it's here somewhere. np.random. Where is that on the sidebar? That's what I want to know. Somewhere on these documentation pages, you got all these array functions and methods. This is one we know about. We've done numpy. Give me the differences of things next to each other. We've done numpy.average or .mean. Those are things. We'll talk about append today, but random.choice, that's the one we really want from that random part of it. It's just like you give it an array. It's a long name, np.random.choice. You give it an array, and it's going to take a few things potentially. It'll give you back by default one thing from your array randomly. Like it flips as many coins as it needs to, or like it rolls as many sides of a die as it needs to, like a 50-sided die if you have 50 things in your array, and it will pick out randomly one thing for you. If you give a second argument, it will start taking that many things. Like give me np.random.choice from this array 3 times, roll a 30-sided die to choose a piece of that array each time. And you might get duplicates. That's fine. All right, that's okay. And then there's also like replace true, replace false. We can get into that later, but not right now. All right, so that's what np.random.choice does. You give it an array of things, and it will randomly pick something out for you. So like you could use it if you're not sure about what to make for dinner. You give it an array of strings, let's say. So let me show that to you. So okay, it's np.random. I've already started a new file. I'm ahead of the game today. np.random.choice. So that's part of this. Import numpy as np. We get that from there. And then you give it an array. Like let's make an array real quick of, I don't know, what could we have for dinner? We could have breakfast for dinner. We could have, on Mondays, I like to make a calzone from Trader Joe's dough. So that's what I'll be making later. What else? I like orange chicken. Very, very big fan of that as well from Costco. So like those 3 things, those are my options. What do I want to have tonight? Apparently that's what I'm going to have. Okay, so that's how you run it each time, right? You rerun it. Well, randomly it was the same thing. Oh, wow, 3 times it was the same thing. 4 times, 5 times. Okay, finally it's different. That was impressively random. But that's what it does. Like it's just going to pick a random thing for you until you tell it to stop. You can ask it to choose a bunch of those things, though. That was the other thing. It's like, all right, give me, I don't know, 5. Pick 5 random times, pick things out of this thing. And so it'll give you back an array, then, of 5 things, each thing picked randomly from this each time. That kind of makes sense? So you might want to use that for things, like that's useful. So that's what np.random.choice does for us. It'll just pick a random element or random elements, giving it back to you as an array of stuff from a sequence. Okay? Very simple, but very powerful. I love it. So yeah, let me just show you a couple examples of that. Like a decent example, like for statistics land would be like, all right, here is like a coin. What is a coin but an array of heads and tails, right? That's all a coin really is, deep down. And if you want to flip your coin, be like np.random.choice from the coin. Using that sequence, go and give me a piece of it. So it randomly picked tails, and you better believe if you reran it, it would probably pick heads eventually. All right, and you can ask it to like flip 42 coins, please, and that's what you get back. You get back an array of it picking randomly from the original sequence each time, which was called coin. All right, so it's like 42 heads or tails, and you better believe if I rerun this, it's a new random sequence. All right, does that make sense? Questions about that? It was very useful. you just give it a sequence, and it will pick a random element for you, and we will go from there. So that's going to be important today. Next, I want to remind us of our comparisons. I know you've used these a bunch already, but just like here's a table with them all. You want to check if something's smaller, you do the less than, right? Less than or equal to, greater than or equal to. You can't like type the little sign like this. So like we've turned that into less than or equal to like that. Okay, so like that's important. We're going to need comparisons. And equality check, remember that's two equal signs. Two equal signs, because otherwise a single equal sign was like setting a value into a variable. That's not an equality check, right? X equals 42. Like give it the value 42 versus X double equals 42. If you want to check if something's not equal, that's the exclamation point equal to. So like 3 is not equal to 2. That is true. It gives you back true, right? 2 is not equal to 2. That question, the answer is no, so it's going to give us back false. So those are our comparisons. So like, hey, is 1 less than 2? Yes, it is. That is true. Is 2 equal to 3? Double equals, right? False. No, it's not. Okay? So, we remembered our comparisons. Does that make sense? Let's come back to us. So you can now combine np.random.choice and comparisons. You can compare arrays to things. So here's something silly. You can ask, all right, here's me, right? I'm flipping a coin 42 times. I'm going to get an array of 42 heads or tails. Here's what arrays can do. You can use a comparison on arrays. Like, hey, is the answer equal to heads? And what this will do is it will take every piece of this resulting array and compare each piece to heads, because it's not just one heads or tails, like it's 42 of them, right? That's what it's going to produce, something like that. It'll go through NumPy, just like when you said this, we'll come back to that. Just like when you say this, right? You have an array, like 1, 2, 3. You can multiply it by 5, right? And it's not doing it to just one thing, it's doing it to all the pieces. Same thing happens when you do a comparison to arrays. So it's doing it to all the pieces at once. And so instead of getting a bunch of heads or tails, you get back a bunch of falses and trues. Does that kind of make sense? So for each piece, like if the first one was apparently tails, it's like, hey, is tails equal to head? False. The next one was apparently heads. Like, hey, is heads equal to heads? True. So it's doing that for each piece. And so now I've got an array of trues and falses rather than heads or tails, because I can do this comparison to each piece of it. Does that make enough sense? It's a little weird to want to do that, but I promise I'm going somewhere with that. So the next silly piece of knowledge is you can treat true like a 1 and false like a 0. Have you ever heard that before? It's an odd idea, like 1 or 0, true or false, off or on, which means you can do math on trues and falses technically. It'd be like true plus false plus true, which is going to be 2, right? Because there's 2 trues. True is 1, false is 0. And with that in mind, we can now do one more library function. It's called np.countNonZero. So if you somehow make an array of trues and falses, you can treat it now, right? Now that we know, you can treat that as like 1s or 0s. False is 0, true is 1. Then you can ask, hey, NumPy, count all the non-zero elements of my array. So like if you had a normal array of numbers, it would work. It'd tell you how many non-zero values were in that array. But it still works if you have an array of trues or falses, which are Boolean values, we say. It's like you can say np.countNonZero, your Boolean array, your array of trues and falses. It will give you back how many trues were in that array. Does that kind of make sense? So that's what we can do now. We can say, hey, NumPy, flip a coin 42 times, check if it was heads, and I'm going to get back, right, an array of trues and falses, which I can treat as 1s or 0s. Python's happy with that. And I can say np.countNonZero, count all the non-zero elements of that resulting array, which is going to give me back a number which corresponds to how many heads I randomly flipped. Does that thought process make sense to us? So this number, this 20, was how many heads then were in this random array of heads and tails. So that's what it got made first. Random array of heads and tails. We compared it to heads. So it's true if it was heads, false if it wasn't. And then we counted all the trues, right? How many heads there were. So it's going to be close to 21, right? Because that's the average of 42 divided by 2. Sometimes it's more, sometimes it's less. But it's about on average, right, it's going to be about 21 heads when you roll 42, not roll, when you flip 42 coins. We're going to get into dice later, so I've got that on my mind. But does this process make sense to us? You make an array, you can fill it with trues and falses, which can be interpreted as ones and zeros, and then you can count how many were there. So in general, or the moral of the story is this next line, the line below, counts how many times we flipped heads. How many times like heads happen. How many heads there were in the 42 coin flip. 42 random coin flips. Can everybody read that? Is it clear enough? It's a weird idea, but like we built our way up to it. Okay? So if we are happy with that, I would like to switch gears to using comparisons to do fancier things. Let's see here. All right, so we're happy with comparisons. We know what they look like. You can do this on arrays now, if you didn't know that before. Next, I want to get to the concept of conditionals in Python. So they look like this. There's a few different options. You can say if something called a condition, and then you give a colon, and then you kind of tab over, or your like Jupyter will do it for you. You give what you want to have happen if that condition was true. So you can be like, if 2 is equal to 2, with 2 equal signs, right? If 2 is equal to 2, do something, if that's true. If, I don't know, if 2 is equal to 3, do something. And there's also an else case. You can be like, if else. If it's true, if this is true, do this. If 2 is equal to 3, do this. It'll never do that. Otherwise, do something else. That's kind of how you can read it. So if a condition is true, do a thing. Else, otherwise, do a different thing. And we use colons and indentation to say what happens. All right, so these are called if statements. So this one's called an if statement just by itself. These are 3 different pieces of code. Like this is a thing. You can do it that way, you can do it that way, or you can do it this way down here. All right. So yeah, let me try to explain this. So what an if statement does is it runs the piece inside of it. We call that the body. Just like we said the body was all the indented stuff in a function. This is called the body of the if. Just like this is the head, I guess, and this is like the meat. What do you want to have happen when your thing runs? So yeah, this particular kind of if statement will do something if this condition that you provide here, which is something that returns true or gives back true or false, you provide something like that there, and then you give some code that you want to have happen if that condition happened to have been true. Maybe it wasn't. Sometimes it's true, sometimes it's false, depending on the data that you're given. Okay, so that's an if statement. Let me show that to you. Like we'll build up. All right. So here. So I'm going to make a function. Well, here, let's make a new section. Conditionals. I'll make a new section for now, and I'll make a function called sign. And what it's meant to do is to take a number x, and it will like give back the sign of a number. Like if you give it a negative number, it'll tell you that it was negative. If you say that you give it a positive number, eventually it'll tell us that it was positive. All right, so that's what it means to take the sign of something. Like what? Are you negative, positive, or 0? So I can say, all right, I got an x value. Somebody's calling me, right? I can do some stuff here eventually. Here's how I want to use this. I'm going to be like sign of negative 42. And I want it to give back that it was negative. So I can say, all right, because x maybe was negative, maybe wasn't, because I can call it sign of positive 42, right? I can say if, how do I notice that this number x was negative? I ask, hey, if x was less than 0. Does that kind of make sense? So that's your condition there. It's like, if that is true about x, the x that I was just given, then here's what I want to do. You hit enter, it automatically indents. And you can give as many lines as you need here to get the job done. I'm just going to need one here. I'm going to say, all right, if x is less than 0, then my answer is to return negative. I'll say that as a string, it was negative. So that can be my function. Does that kind of make sense? I can call sign of negative 42. And it really will give me back negative because it notices that x gets to be negative 42. It's like, is negative 42 less than 0? Yes. So it runs all this code in the body of the if, we say. All right. And then we've had it like, and it skips everything in here. It does not give back anything at all if x was not negative. Because it's only if this is true do we go and run this line. So if I say, hey, what's the sign of 5? We get nothing at all. Because from that function call's perspective, we did not hit here. We just kind of fell through and did nothing. Does that make sense? Are there any questions about that? It's a little subtle, but that's what it means to be an if statement. You give us some sort of condition here. Usually it's variable, right? It involves the variable's value. And then you indent and you give all the lines that you want to have happen if that particular condition was true this time. Maybe next time it's not, but this time, if it was true, run all these lines, as many as indented things that you want to give here. Any questions about that before we do if-else? All right, so right now it's only hitting this. Like only if it's less than 0, it runs this line, it runs the body of the if here, and like gives back negative. Otherwise, it skips it, right? If this is not true, like 5 gets passed in for x. Is 5 less than 0? No, false. So it does not run the body here. And that just completes the execution of the whole if. And so it just skips everything, does nothing at all. All right? So let's update this. Let's do an if-else. An if-else is, it runs, we call it the true branch and the false branch. If the condition is true, we run this, all these lines. And if it's false, it skips to the else. So it does do one or the other at that point. And it runs all the lines if it was false. That's perfect. So sometimes you want to do one thing if it's true, another thing if it's false. That's what you'd use an if-else for. So let me update the sign function. It's like, all right, if x is less than 0, I'll return negative. Else, otherwise, if it's not, let's say, we can't say positive here because it could have been 0, right? Does that make sense? We can't say positive here. We can say non-negative. That's slightly better. But that would be our if-else. And now it will work for any number that we could possibly give. Like if this is true, we say it's negative because it's less than 0. Otherwise, we'll give back non-negative. You see how we're always going to hit one of these cases now that we have that else? We're always getting one or the other. So I can say sine of negative 42, that's still fine. I can say sine of 5 now, non-negative. For this one, x gets passed into here. Hey, is x less than 0? It asks that question first. True for negative 42? Yes, it is. And so it runs this one. It's always one or the other. It picks the one that works. If it's true, it hits this one. If it's false, it hits this one. So like when it's 5, it's like, hey, is 5 less than 0? No, it's not. So it skips the body of the true branch and runs the body of the false branch, we say. All right? This is called the true branch. And this is called the false branch. Because it's kind of, if you think of it like the branches of a tree, it's like you can either go this way or this way in your universe of your program. And so it's one way or the other. All right? And so now it's happy. It's always going to do something now. Our function's never going to like give nothing back. It's always going to hit this one or this one, because if this wasn't true, it hits this. You can kind of read else as like otherwise. Okay? Questions about that? You see the vision? Because there's a slightly more complicated one that has multiple conditions, and I need to get to that now, if we're ready. Ready for the addition of the elif? This one gets a little confusing. So sometimes you have like a checklist. It's like, if this is true, I want to do this. Otherwise, if that wasn't true, then I want to go and try my next highest priority thing. It's always like there's like a priority order going on. And so that's what an if-elif does for you. It's like if condition 1 is true, here's kind of how this works. You give your first condition, like that's your highest priority thing. Like you want to run this code if you can. This is like highest priority. This is like your next highest priority. Whee. And it's gonna find the first one that works, essentially. It's like, all right, it tries this one. If it's true, it runs this, and it's done with the whole darn thing. These are all connected to one another. So it's just gonna find the first one that works. All right. If this one's happy, it runs this line, and it's done with a whole if, elif, else. All right. Otherwise, you can read elif just like else as otherwise. Otherwise, if this first one was not true, if it was false, like it was negative or something, or was positive or something, then you can go to the elif. Elif is short for else if, by the way. It's like otherwise if. You can read it like that. Otherwise, maybe condition 2 is true. That's your next highest priority thing. Condition 1 wasn't true, but maybe condition 2 is true. If it is, it will run the body here. You give another colon, you tab over, and you run this code. If that checks out, you're now done with the whole thing again. It's going to find the first body. It runs the first body of the first true condition. first true condition runs, and that is all. And you can chain as many elifs as you want. You can have another elif here, more elifs here with other things, other priorities things. All right, I'll give you some examples of that in a second. But like that's what you can shove there. If you have more things, like if this is true to this, if this is true, otherwise if this is true to this, otherwise if that's true to this, all the way down to the else. The else is when you give up. The else is your final otherwise, like, all right, there's no condition attached to it. It's like if none of the other above conditions worked out, if nobody works out, if no conditions at all work out above you, there's like this is like your fall through, your fail safe. If no conditions work, then like this is, you're making sure to do something at least. Usually you want an else. But that's kind of how it's going to work. It's going to run the first one that works, and that's that. Okay, so let's fix our sign function now with an elif to have like negative, positive, and 0, right? Because that's the secret third option. So let's do that. And then maybe I'll give you like a longer example there. So, okay. Instead of negative and non-negative, well, let's think of it this way. It's either negative, positive, or 0. So let's add another option. So like, all right, this covers if it was negative. That one's fine. And I can say elif. Otherwise, this is like option 1, option 2. Otherwise, maybe x was greater than 0. See how that covers another option there? Otherwise, maybe that's true. If it is true, then I will say the answer for me is positive. Does that make sense? How I can do it that way? It's like, all right, if it's negative, x is less than 0 that I was given, do this. If it was positive, otherwise, do this. And then we can have our fail-safe case. We'll only ever get here, right, if it wasn't negative and it wasn't positive. What's our last option? See how 0 is the last option? Like, all right, that's not true when it's 0. That's not true when it's 0. We will come here, but only when it's 0. Yeah, that's how that works. And so that's it. We can be like neither or 0, whatever you want to say, something like that. So notice how the only other option is x is equal to 0. So this could have been an elif. Be like elif x is 0. That would have also worked, and you can skip the else because there's no need for an else at that point. But we'll just say else is faster. Okay. Are there any questions about this code and what it's going to do? See how it's going to try, it's going to run the first option that worked. For us, luckily, none of these overlap. But if any of these conditions overlapped, it will find the first one that works. Always the first one, and that's it. Okay? And that's how that is. And now I can say sine of positive 42, sine of negative 42, sine of 0. We got them all. Everybody's happy. All right, and it just finds the first one that works. Any questions about that now that you've seen it happen? See how it's running the right stuff? So it's thinking. We can branch off. We can do one thing or another, potentially 3 things, right? A good example of a bunch of elifs is like a grade calculator. Be like, you give me your grade. Grade is, I don't know, 75.5. And there's like a priority order if you think about it. It's like, all right, if the grade is greater than or equal to 90, then like it's an A, right? We can print A. We'll use the print function to just show stuff. Otherwise, if the grade was greater than or equal to 80, print B. And now the order is very important, right? It's like, okay, if it was greater than, like, you don't want to do this one first because 90 is greater than or equal to 80, right? Can't do that one first and think it's a B accidentally. So just stare at that for a second, you'll get it. Otherwise, if the grade is greater than or equal to 70, print that it's a C. Elif. Otherwise, if the grade is greater than or equal to 60, if that, print AD. And the reason this is going to, otherwise, it was below it all, printf. The reason that this code will work and give back C or print C is because of the order, right? It's like, all right, 75.5, is it greater than 90? No. All right, try this one. Is 75.5 greater than or equal to 80? No. Is it greater than or equal to 70? Yes. So it does that one, and then it's done with everybody. It finds the first one that works. Okay? Questions about that? You see it now? Like, that's why you might want to have more than 3. So that is useful knowledge. Yeah, is that a good enough example? Are there any questions about ifs? Like, you can do an if alone. It's like, up here. Do something if it's true, do nothing at all if it's not true. If else is like do something if it's true, something else if it's false. And then if else, that's like the ultimate power. You have as many else as you need. It's like something if that condition is true. Otherwise, try this condition all the way down the line until the else. That's your fail-safe, your fall through. All right, I just have some examples to show you, and then I'm going to ask you to try it too. So like try to have it soak in. Ask me lots of questions as they come up. But another thing that we can do now, which is kind of fun because we have randomness and conditions, is we can make a guess the number game. I think that's pretty fun. So here, let's do that. Guess the number game. So to make a guess the number game that is fun, we have to come up with we have to tell Jupiter to think of a number for us without actually telling us that number, right? So we can use np.random.choice for that and be like, all right, the secret number equals np.random.choice, and let's make it guess a secret number from 1 to 100, let's say. And so we just need to supply an array of the numbers 1 to 100 right now, and it will pick a random one for us. And it won't tell us as long as we don't try to print that value, right? And so to make very quickly the numbers 1 through 100, that's the np.arange, remember that? So give me an array range, please, starting at 1, going up to 101, right? Because it's not including the last thing. It's going by ones by default, though. So this is now the array of 1 to 100. And here it is picking a random value. And as long as I don't ask for whatever that random value was, as long as I don't say secret number, Shift-Enter, I won't know, right? And it'll be fun. And it's different every time you rerun the cell. So that's kind of cool. So okay, I want to be allowed to make a bunch of guesses, and I'll make a function for that. Like def, my guess this time was the number n. So I'll make a function to keep track of my guess, whatever it was right now, and compare it against the secret number and give me hints, right? Because that's kind of how the game works. Like you guess a number, and they tell you if it's too high or too low, or if you got it. So all right, how do we want Jupiter to play this game? It's like, all right, we guess the number n, right? So like the very first guess, we'll say our guess is 50, something like that. So that's the best guess for the number game from 1 to 100. So like n is going to have the number 50 the very first time. And what we want to do is always just compare what we were given, like if, to the secret number. So like if n was, I don't know, bigger than the secret number, like we guessed 50, but the secret number was 25, then we want to give a hint to ourselves. We don't want to give ourselves the answer, but give us a hint. Like, all right, if that's true, like we guessed 50, but the secret number was 25, will be in this branch. What do we want to do? We can return what to do as a string. We can say, all right, you guessed too high, right? See how that's the hint for that case? Does that make sense? We're just comparing what we got to the secret number. And then we can do the other one, right? Elif, right? Otherwise, maybe it wasn't too big, maybe it was too small. Maybe our number n was smaller than the secret number. It's like we guessed 50, but it was really 75. We can say too low, right? And just like for the sign case, if it wasn't too big or too small, it was just right, right? So otherwise, return, you got it. Something like that. And I think that's what I wanted to say. Yeah. Does that guess function make sense to us? What it's going to do? It's going to compare this number that we're asking the user to give us to the secret number, and it will give us a hint each time we call it. All right? But it keeps the secret number, as long as we don't rerun this cell, it'll keep the secret number the same value as it was. So rerun this cell when you want a new game. But now I can say guess 50, and it's like, oh, that's amazing. Wow, that'll never happen again, but I'm glad you guys got to see that. So I rerun the cell and try again. It's like, okay, now it was too high. Okay, so you can keep playing. So whatever the secret value is, as long as I don't rerun the cell, it'll stay whatever the secret one was. So like too high, okay, maybe 25. Oh, okay, still too high. It's a small number this time. We'll be like, all right, 12. It's kind of in 12 or 13, right? Too high. Wow, it's a small number this time. 5. Too low. 8. Too high. Either 7 or 6, right? Oh, it's 6. Nice. Yay. So that's kind of fun, right? You can do that now. I love that. I love that for us. Are there any questions about how this works? Yeah.
So until you rerun the function, the number will stay the same.
That's right. Really, I could have split this up into two separate cells because this is the function never needed to change. The function is always correct, but it's this variable's value that is the secret number. So as long as you don't ever rerun this line, it will never pick a new secret number. Yeah. Other questions? I think that's useful and fun. What else? Randomness and statistics, right? They were invented because people loved to gamble back in the day. So like we can think about that if we'd like to. There's I don't know too much about it, but like this thing, roulette. Have any of us ever played this? Because I have not. Like you can bet on red, or you can bet on a number, red or black, or sometimes it's green, the 0 zeros. That's how it's like guaranteed that you'll eventually lose money. But you can make a table of like all your options for some sort of casino game. And so that's something that people have done. We have a data set file here for, let's see, dun, dun, dun. It's called roulette wheel. And so let me read in that table and we can think about it. Because all we need to use randomness, right, is to get an array. And you can totally get an array from a column of a table, right? So give me the roulette wheel. Roulette. That is table.read table data roulette wheel. Something like that. So there it is. All right. Dun, dun, dun. So you got pocket and color apparently. So pocket is the number and the color of the pocket is what's associated with it. So like 1, 0. I think there's also a double 0 and it's just not shown because of the way this table thing works. But you got 1 is red, 2 is black, and then I think it alternates until the highest number. And so if we want to make a bet on a color, we can use this color column to like pick a random one. Be like, all right, we roll our little thing, roll the roulette wheel and put the ball in or whatever. We can simulate where it might stop. We can be like, all right, give me roulette dot column, call it color, right? Give me the color column, and now that's an array that I can mess with, right? I can say np dot random dot choice, or if I don't want to type color, remember you can use the index. This is index 0, so index 1 is the color column. Like boop, give me that, and then give me a random choice from that, np.random.choice. And so like you can simulate, okay, if you bet on black, you would have won just now, something like that. And so you can make some interesting simulations, which we'll get into soon. But like, let's make a function called like, all right, let's say that our favorite color is red, and we want to bet on red a bunch of times. Let's kind of see what would happen if we were to play roulette enough times. So okay, I'll make a function called, let's say, I'm going to make one bet on red. That's the example. And I'm going to bet a certain amount of money, which I will call AMT for short. All right. And so I had to look up in the book how this works. This is their example. So we can use this again, right? The color that we got, whatever the color was, it might not have been red, but we're pretending to bet on red right now. So that the actual answer, the color that we're getting right now, is this random choice, right, from the roulette wheel and all the colors in it, all our options. And if the color is red, if you bet on a color apparently, you get back your money. Like you win your money back, and also on top of that, you win the same amount again. So like if you bet $1, you will earn back the dollar and get another $1 if you won. Apparently, that's how it works. So like your winnings is like you get your amount back, kind of. So let's say that that's how that works. And otherwise, you lose that amount. So like I guess your winnings is a negative number. So like whatever you just bet, you get that back times -1. That is your winnings in a sense. Okay, so I think that's what I wanted to say. So like if you bet on red and it is red, it happened to be red, it's as if your dollar never went away. You get back, like your net profit is one unit of whatever this was. If you bet $2, you get 2 back, right? Whatever the amount was. But otherwise, you lose that money. You're in the red, in the other sense. So times -1. Okay, so that's that function. And so we can call it a bunch of times, like to simulate what might have happened. So let's just repeatedly bet a bunch, like a single dollar each time on red. And I can call it a bunch of times and get back a bunch of values by putting commas between my calls, and it'll just give me back a bunch of answers all at once. So it's calling the function secretly 4 times, and it's going to give me back like a kind of a sequence of the answers. So apparently I won all 4 times. Good for me. But we know that will not always happen. If you keep on rerunning it, it's a bunch of different random answers 4 times. So like this is like a little simulation of our game. Yes.
Would it work if we were to give it in random dot choice multiple guesses, I guess?
That would also work. It would change the way that this function would work, though. So you'd have to maybe want to pass like how many number of the bets I want to make right now.
If you put in there and then let that column afterward, you put like comma 5.
Yeah.
The function still work?
The function would still work, but think about what you're getting back in color now. You're going to get back a bunch, you're going to get back an array of colors. Like sometimes it's like red, 5 of them. Red, black, green, black, red.
So it will give you an array of how many columns you have?
Not quite. So think about, like, let's follow that through. Like, okay, once I have that and I compare it to red now, I'm going to get back a bunch of trues or falses. So now, like, it's going to be a weird result there for the quality check. Does that make sense? And so, like, this is no longer something that is true and false. It's got a bunch of mini trues and falses.
Mm-hmm.
So our condition kind of doesn't really work anymore, if that makes sense. But there is a way to turn the falses into negative ones and the trues into positive ones. So they already are. And then you could like do a summation after all like that. There's a way to make it work, if that makes sense. Does that kind of answer your question for what you want to do there? Yeah, that is an interesting idea. Any other questions? That's a good one. So there's a way you could change the function to have that work in a way. Yeah. So yeah, this will seems like you can pretend this all works. So like if you want to, I don't know, if you need random numbers for something one day, you can come to Jupyter and make it work. So there's that. Like you're playing Dungeons and Dragons or something. Like you need to roll a certain sided die. You can totally use np.random.choice for that. For example, like we did roulette, let's do a single die. So like np.arange. What are the sides of a standard die? It's 1 through 6, right? So make me arrange 1 through 6 by saying np.arange 1 7, because it's always got to be up to but not including that last one. And like that counts as your die roll. And so like you can always do that and change that to 21 if you want a 20-sided die. All right, and apparently we got 4. Cool. I think that's most of what I wanted to say about conditionals. Any questions before I force you to try? All right, I'll give you this. This is our sine function. It's kind of fun. What else? There's also the secret number function. That would also work. But here's my question for you. So here's the silly example. We'll use Goldilocks, the childhood fairy tale, as an example. So I would like you to please, in the same vein, try to make a porridge rating function that takes how hot the porridge was from the silly story, and it returns back it was too hot if the temperature was greater than 150. Returns back too cold if the temperature was less than 100, because like that's not good, right? Our tongue can tell the difference. And then just right if it's right in between, right? That's like the sweet spot where it's the perfect temperature, apparently, or so my mind thinks. We'll have to figure this out. But yeah, let's pretend that those are the right numbers. That's the optimal temperature for porridge. So please try to, in the same way as I made the sine function, make a porridge rating function that you can call with a given temperature. And it will tell you if it was a good one or not. Okay, questions about the question? So please give that a try. And I will be here to answer your questions if you have any, but I'll give you like a 4 or 5 minute head start. Please help each other. You don't have to post this anywhere. I just want you to try to make it and try it yourself. Question?
Is 4 moving in the data set, or is it just like you want to make it?
Oh, it's not a table, it's a function. I want you to make a function that just like sine wasn't anything in the
Or
file.
like reading in a table or anything like that?
No, you're going to call it with a single number. That was the temperature of right now, whatever the porridge was. Cool, look at that. And then we got... Some of these could be in a certain order. Technically, you can do these in any order if you knew a trick that I don't know if I'll be teaching you anytime soon in this class. So one of these might have to be an else, or at least like your order of conditions needs to be important for at least one of them. And your parameter variable does not have to be called x. You can be like, you can call it temperature or something. Use a name that makes sense to you. Why do I have to do that? All right, that was my timer at least. Do we want another minute to keep trying? Or is that enough time? Speak now. I'll show you how I think about it. Again, you probably could have done this in a few different orders, but at least to me, this is just right. If I pick the right order, this can be the last one. Does that kind of make sense? Like if this is true, if it's greater than 150, it's too hot. If it's less than 100, you can keep this order. You could have done the first two flipped. That's fine. But do you see how the opposite of both of these, like, all right, if it's not that, then it must be less than or equal to 150. And if it's not this, it must be greater than or equal to 100. That gives you this. That's why I made this into the question. But I think this would be a good else. Does that make sense to us? I think that would be a very easy, this can be our last else case. All right, else that. Because that, we get it for free. It's just the opposite of these two, right? Because if it's not this, the opposite of greater than 150 is less than or equal to 150. And the opposite of less than 100 is greater than or equal to 100. And so, yeah, if both of those fail, we know that that's true about our number, right? That's true about it. So that's perfect. Let's try that. Okay. Oh, completely wrong spot. Here we go. So I will say, I don't know, def porridge rating. And in my sign example, I called it X. In our guess example, we called it N. But whatever you put here is just the value that you got from the user as they called your function. Call it whatever you'd like, just any variable name. I'll call it temp for temperature. So if the temperature, let me do it backwards so that you can see it works either way. So let me swap too cold and too hot, because it could have been in any order for those first two at least. Like if the temperature was less than 100, then it is too cold, right? Does that make sense so far? Just gotta be consistent. Like I called the thing that I got temp. I gotta say that now. So if that's true about temp, it was too cold. Otherwise, elif, if temp was greater than 150, then it's too hot. And then finally, otherwise, if none of those are true, that means it must have been, right? Think about that. If this was false, right? The only reason we got here is if this was false and this was false, which means that it must have been greater than or equal to 100 and less than or equal to 150. Oh, goody, that's just what I needed. All right, so just right. And so that will be my function. Does that make sense? Questions about that? It should work for everybody. Like if it was too cold, like it was only 95 degrees, too cold. If it was 175 degrees, too hot. But right when it's 150 or less, in between, right? It's just right. 125, maybe that's the optimal porridge temperature. I don't know. Depends on your tongue. But that is, that's how you can call it, and that's how it would work. Any questions that you've seen the answer, or at least one way to get at the answer? You could have swapped these first two for sure. Could have kept it in the original order, but like this is perfect as our else case. It's kind of hard to do it in a different way. It's kind of hard to put this one anywhere but last without some extra knowledge that you'll get one day. I think that's a good example. So we happy enough with conditionals? Are we ready to switch gears to something slightly different? All right, so you guys get something interesting. I don't think I've ever, maybe in a CSI 1 class, but never in like a major level computer science class do I teach both of these things on the same day. But for us, we need them both, and it makes sense to do both of them. So I'd like to teach you about what's called a loop. All right, so a loop is something similar. It's just like a function, just like an if-else statement. Like it's got a thing with a colon and it like has a body. It still looks like all that. But what a loop does, as you can imagine, right? It's trying to do that. It's trying to wrap back around. So what a loop does is it's going to go through something. It's going to go through something in it as many times as there is something to go through. And for us, that means we'd like to use it for sequences. So I'm going to teach you something called a for loop because the word starts with for, just like this was called an if statement because it started with if. But this is called a for loop, all right? Because it starts with the word for, and it's trying to say, I'd like to go and do something for every value in a sequence. That's why you use the word for, I guess. So this is kind of how it looks. You say for gives any name of a variable here. This is just a variable name, whatever you want it to be called. And you say in. For every variable name called I, I'll call the thing I, in this thing. This is your sequence that you want to go through. All right, so sequence you want to go through. Go through. And some people say, and I'll say it too, that you're going to iterate through the sequence. Iterate is just a fancy college level word that means to go, right? Because it comes from the Latin root iterate, right? Like your itinerary, stuff like that. So just like we're going through this thing. And so how this loop is going to run is it's going to, like this is a sequence from 1 to 10, right? What it will do is it will let I be the next value in that sequence. It's going to set that variable. It's going to say like I equals 1 the very first time because that's the first value in the sequence. And it's going to run the body with I set to that, if that makes sense. It's like the very first time, this is kind of how, this is a general case, for variable name in range, your variable name gets set to the next thing in the range as long as there's a next thing, the first thing if it's the first time. And it runs the body, all this, right? That's your body, as many lines as you need. Using this variable's value, you do stuff. So here's the body of the for loop. Body again. Okay, as many lines as you need, as long as they're indented. So let me kind of walk you through how this function is going to run, or not function, excuse me, the loop. So you got this I variable. It does not exist yet, but it exists for the loop. So for I in this range from 1 to 10. So the range is from 1 to 10. The very first value that I is going to get set to, because it's going to go through every possible value in the sequence, is 1. So Python is going to set this I variable, it's going to create it and set it to 1 and run the body once with 1, and it will print the number 1. Does that kind of make sense what it's going to do the very first time? It's going to pick out the next value always, put it in that variable, and run the code of the body of the loop with that new value. So the very first thing it's going to do is print 1 to our output. And then it's going to come back around. It's like, as long as there's something I haven't seen yet, it's going to go in order from left to right. As long as there's something I haven't seen yet in this sequence, then I'm going to keep going. So the next element of this array, right, it's the array from 1 to 10. The next element is 2. And so it will set next I to be 2. That's what it will do. And then it will run this code again. It's going to loop through. It's going to run that code as many times as we have something in our sequence. All right. in our range of things. So then it's going to say, all right, I is 2, run the same code. It repeats the code. That's what a loop does. It repeats things. And it will, all right, with I being 2, how does this change? Well, it prints whatever I is. Now it's going to print 2. So now it's printed 1 and then 2. Does that make sense? And so I think you can extrapolate now. Like I is going to be set to 3 the next time. It'll run it again, print 3. I is going to be set to 4 because that's the next element in the sequence. Next time, print the 4. All the way down to it will be 10 the last time, right? And then we'll print the 10. And then at that point, Python notices that the sequence has been exhausted. I've gone through every value. I've gone through 1 to 10. I's had a chance at being all of them. We've run the body with every possible value of the sequence. Then the loop is finished. Then there's no more need to repeat. There's nothing left to repeat. All right, we've gone through every value. We've iterated through the whole thing, we say. Okay, so this code is going to print from 1 to 10. Do you see it? Do you see why it will do that? Print all of those values. Let me show that to you. So these are called loops. They repeat code. So this body here, this code of the body of this loop is being repeated multiple times with different values for I, though. That's the whole point. Because it would have been a whole lot of typing, a whole lot more typing to say print 1, enter, print 2, enter. Especially if it was like 1 to 100, you say 101 here, and now suddenly you're printing from 1 to 100, aren't you? That's kind of nice. So that is a loop. Beep. And you can go through anything. It doesn't have to be just numbers, but here, let's do this one first. 4, dun, dun, dun. Let me actually just type out. So for every value, I'll call it each value I, in the range from, so it's np.a range from 1 to 10, so 1, comma 11 there. And you can go to anything else. It'll be like 1, comma 101 to go from 1 to 100. And what do I want to do with each value of I that's taken from that sequence in order? I want to print it. You can do other things with it. It'd be like print I times 2. Then it goes and it prints out the even numbers, right? Something like that. But there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I was running this line 10 times, 1 for each value of the sequence. I gets a chance at being all of those values. Okay? Questions about that? See it? So you can go through things that is just as long as there's a sequence somewhere. So it doesn't have to be a sequence of numbers. Be like, let's have an array called people, or like an array of people, like me. My name can be in it. My cat's name can be in it. Bill, the other computer science professor here, his name can be in it. We can say, for every, call it person, use a variable called person in this array. For every, see how you can kind of read it in kind of like English. It's like, for every person in this array, do something with that person. Like, let's print them out, print person. So like you can do math on things if it's mathematical, but like you're getting each value, okay? And you can do something fancy with it, like, I don't know, times 3. It's just saying it 3 times, computing a new string, right? But again, it's going to run this code, whatever you put here, indented, for each element of the sequence in order from left to right. Okay, you kind of see what's happening there? So remember that np.arange is really just a sequence, right? It's just a sequence. It is an array deep down, even though we didn't explicitly say it. It's this array from 1 to 10. Okay, so that's us computing it on the fly. Any questions about any of that? So that's loops in a nutshell. That's honestly all that I wanted to show you. It's like you have some code that you run repeatedly, 1 time for each value of your sequence. And so because it's a different value each time, you got to give a variable's name because it's going to be something different. Usually, I guess you could have an array of the same thing a bunch of times, but that might be a little silly in most of the cases. All right. So yeah, taking this code, I want you to try to do things yourself. All right. Try to. I guess there's two options. I kind of already showed you one way. Think of another way. You can change how you make the range. Try to make a loop that will print by 5s. 5, 10, all the way to 50. Yeah? See if you can try that. I'll give you a few minutes to try, and do ask me questions if you have any, but like, take that code. How can you do it differently? I can think of 2 ways to do this. Somehow make a sequence you want to go through, and you want to do something to each value of that sequence. It would be as simple as just printing. another minute or so. It looks like we're mostly there. Yeah, try to extrapolate if you got it already. Try to go from 5 to 100. Try to count by sevens. Like, see if you can fully understand what's going on here. Print downwards, like -5 all the way to -50. How would you generate that sequence or modify another sequence to create it? Ooh, maybe I can think of 3 ways now. Cool. Yeah, a few more seconds to try, and then I'll show you my answer, my thoughts. That is very, very loud. All right, I think that's what I wanted to say. And I'll check those later. All right, so let us take a look here. I think in my mind, the simplest way to do this would just be to change the way the sequence works. That's where my brain goes just immediately. It's like, all right, instead of, I guess I'll take it from here. Instead of doing it from 1 to 10, I'll just go from 5 to 51, but by 5s. Remember how to do that? That secret third argument to a range? That'll work. Did anybody else do something different? Yeah.
I did for num in NP range 1 to 11 and then print num times 5.
Good. Yeah, you could have done the same thing as we did here, but instead of just printing I, you could have printed I times 5, because like 1 times 5 is 5, 2 times 5 is 10. That totally would have worked. A secret third option that I thought of while you guys were doing it was like, you could have started with this. You could have said for I in range this times 5, couldn't you? That would also work. Could have made a bigger array using the multiplication of a smaller array. That's cool too. So like then you go through that and you print all the values. Because I guess that gives you exactly this. Cool. So that's another way to think about it. So yeah, a bunch of different options. There's one. Any questions about the question? We comfortable enough with loops? Because we're going to need those a lot. We want to like flip a coin a bunch of times and then like determine how much money we won, like and add to a count, a running count. Like that's going to need a loop. It's not just np.choice, np.random.choice. We want to do some conditions based on what we just rolled on our die or flipped in our coin. So that's where we're going. Are we ready? That's what we need. So we have the power now, all right? Which is great. So, okay. Let's see, how do I want to do this? So, yeah, I guess in general, we can now use the combination of loops and randomness to essentially simulate a lot of processes, including playing roulette, including playing a bunch of different like games that you might find at a casino, things like that. So let's go back to roulette. We'll also do coin flipping, but let's do some simulations where we do some interesting ideas. All right, I'll get to that. So I want to talk about how to simulate things now, because we kind of started with that, right? This kind of like, I called it 4 times. We can now call it 1,000 times in a loop. All right, that's where we're going. So, okay. Simulation. Boop. So, okay. Here is something interesting. We know that this loop is going to go through the numbers 1 through 10 and do something with it. Another way to make, well, it's going to run its body 10 times is another way to think about this code. Does that make sense to us? Like we've made this sequence that's 10 things long. It's going to run its body 10 times exactly. Okay, so that's kind of interesting. So I can say my one bet on red function, I can call that like, let's make one bet 10 times. Print. So now I'm going through this sequence of 10 things, calling that function each time and like printing out its answer. Does it kind of make sense how I'm just using the size of that sequence now? It's like, all right, there's 10 things in it. So that kind of guaranteed that I ran my one bet on red function and printed out the answer 10 times. Does that make sense? So it could have been like, go from 5 to 15 or 16. I don't actually remember. 16. I would get the same, no, it was 15, sorry. No matter what you put here, like I'm just using this to do it 10 times. All right, so a quicker way is just like, give me a range with 10 things in it. That by default, it goes from 0 to this number minus 1. So it goes from 0 to 9, but it's still 10 times. All right, so that's a quick way to make a loop that goes through 10 things. I'm not even using I. You have to put a variable name there, but it's just like, do it. Do this thing 10 times. That's what this loop is doing. I really just care about running this line exactly 10 times. Does that make any sense? That's how you do it. All right. Even though I'm not using I. I'm not using I here. The loop just ensures, or it's just running 10 times. I'm running the body exactly 10 times. That's all I really care about. Okay. And so now I know that I could run this function a bunch of different times, and sometimes I get a different value, right? It's random. It's a game of chance, right? So we can keep track of, we can play 100 games of roulette now. We know how. We just do np.arange 100. We can use this function to get back an answer. We can compare that answer, right? Or just like add it to a sum or something. So here's something that we can do. We're like, all right, at the beginning of time, we've won nothing, right? Our winnings, I'll make a variable called winnings that starts at 0. So at the beginning of time, when we walk into the casino, we've won nothing at all. And then let us place 100 bets on red. All right, we'll be like for I in np.arange 100. So this is going to run its body 100 times. I don't have to use I, I'm just using it to do the looping. I can make one bet, right, on red with one, I'll bet $1 each time. That's me making 100. I'm essentially calling this function, one bet on red 100 times. Does that make sense so far? That's what's happening because it's being repeated. It's being repeated as many times as there is something in this array, which is going from 0 to 99. And so each time I've got a value. It's going to be 1 or -1 in our case, but it depends on what you pass. It would have been 5 or -5 if we did it this way. But I've got a value. Like that's how much I won or lost. And I can say, hey, winnings, set your answer equal to what you used to be, right? Because you want to remember what you had. Like you have so much money, like you're either winning more or winning less. It's like, all right, I would like you to add my win or loss to winnings and store that back into winnings. Like if it was 5, like if winnings was 5 right now, it's like take the 5 and maybe I just won 1. Take the 5 and the 1, now it's 6. That's my new amount of winnings. Does that make sense? It's always adding in the new value 100 times. And so this will affect the winnings variable 100 times. It's just taking whatever was there, because you remember when you do the assignment statement, it's always doing the right-hand side first. So it's taking the old value, computing a new value, and updating the winnings variable. So this is updating the winnings variable. It's adding in the answer, right? It's accumulating a value. Accumulating the sum of all of our winnings. That's how you can think of it. It's like, all right, what was the old value? Add in the new one or -1 from our win or loss. Add that back into winnings. So now that's the new value. So at the end of all this, the winnings variable holds however much we want. So it looks like this time we didn't win too much. -4, -12, -8. Ooh, we were lucky that time, but not. Usually you're going to be losing by the time you leave the casino, right? So does it make sense how this winnings variable is being affected 100 times? It's essentially as if this loop, all it is more or less this line copied and pasted 100 times. Does that make sense to us? Because that's secretly what's happening right there. It's really, all this loop is doing is going 100 times and running this code. That's what's happening. It's updating the winnings variable. Okay? Any questions about that? It's an interesting idea. We've just simulated 100 games of roulette. And usually you win, apparently. Or usually you lose, excuse me. So that's kind of fun. There is, because people love to use variables like this. They want to like add in an answer, take the old value, add in the new thing. There's some shorthand for that, and I might show that to you one day, so I want to show that to you now. So you could have said, if I had like an x variable, x equals 42, I can give it a new value by saying x equals x plus 1, or shorthand for that is x plus equals 1. It's like add in a new value, add in the 1 into itself. All right? I can't remember if the book has shown that to you yet, but there you go. Or if I've shown it to you yet, but that's another way. This is equivalent, this line equivalent to the above. It's just like adds in a value into x. Okay? So for this line, I could have said winnings plus equals 1 bet on red 1. Okay? Could have been that. Could have been that. And so now the value of x is going to be 44. Because I did it once that way, it adds in 1. Okay? So that's our first simulation. Are there any questions about that? We're keeping track of a value that's important to us, like how much money did we win? All right, you got to start it at 0 though. Give it an initial value. That's very important. We have to give it an initial value to start us all off. So, and then we take it from there. Ready for another example? We can do some cooler analysis with an extra piece. It's another function. Luckily, it's right next to, like this all goes in order in the documentation, which is great. There's this mp.append. So what mp.append does, usually you add one thing only, but you could add a bunch of arrays at once with append. Append is like you're attaching to an existing array. So what you do is you give it an array and a new value, all right? And what it will give back to you is a copy, a new copy. Usually you put it right back into the old value. But it will give you a new array with the old array, all the same things that were in it, with the item at the end of it, the new thing at the end of it. So it's a way to extend your array by one value. So you had, this was your array, if you say np.append with that array's name and a new value, it will compute and give back to you this bigger array with one more thing in it. Does that make sense? So it does not affect the old value of this array. If you want that to be, if you want this whole brand new thing to be that array, now you got to set it into that again. So it's just kind of like the table methods and functions in that sense. Okay, so let me show that to you. Let's say I've got an array called A. 1, 2, 3 is what's in it. Here, I'll have it printed out. Like this is legitimately an array with 1, 2, and 3 in it. I can say np.append, np.append to A, the value 4, if I want to make it 1, 2, 3, 4, right? So there it is. I've got 1, 2. It will give me back then the array with all these values, but with the 4 at the end. Okay? That's how you extend your array. But by default, that does not change the old array. It gives you back a copy, this creates a brand new array, just like all your table functions and methods, with the new answer attached. But the old one is left untouched. So if you wanted like, oh, this should be my array now, you can take this code and be like, all right, its result, store it back into A. Does that make sense? Because now it really will be the array 1, 2, 3, 4. And you can do that a few times. Like A equals, like append whatever it used to be with that, append 5 at the end of that. Like that's how you can add values. That's the pattern. So now array really holds 1, 2, 3, 4, 5, because from this line, it made the array 1, 2, 3, 4, put it back into A. And so now we're in this next line, we're appending to 1, 2, 3, 4, the 5. So now it's 1, 2, 3, 4, 5, and then shoving that back into A. Or A really is that now, as long as you keep on using that assignment. Okay? Does that make sense? You can add a value one at a time to an array. Usually that's all we're going to do in this class. You can also use append to attach 2 arrays to each other if you wanted to. It will just give you the bigger array with each value. So let's see, what do I want to do? So instead of printing out now, like our bets, or keeping track of our winnings in a single variable, we can have a bit more of a an interesting time. We can do more interesting things now if we keep track of like what was each winning for each run of the game. So I'm gonna start with this. I'm I'll call it this instead. So we can play the game this way. Like, initially, I have no winnings or losings. I'll just make an empty array. Make array with nothing, just like makes it an empty array that hasn't held anything yet. And instead of saying winnings equal, like treating it like a number and adding on my value, I can append to winnings. It's an array of all the things I've won or lost, one at a time. So I'll have a bunch of different elements for each game that I played here. I can say np.append to winnings, the result of my betting for this particular round of the game, and set that back into winnings. And it's more interesting to just show you what's about to happen. But think about what is going to be stored into winnings now. Think about the values that it will hold. It's going to be an array of 100 elements. Each time, right, we added this thing, which is either ever going to be 1 or -1. It's like that was the actual sequence. Like the first time we won, the second time we didn't win. We get more information this way, right? Rather than in that one variable that just gave us the final total. So you can still create this answer like we did in this way. That's just now the sum of this array, right? But we can also do other things now too. That's more interesting. So we can say like, give me the sum of all our winnings. Apparently we didn't do very well. You can do that, but you can also do other array things, can't you? You can be like np dot, what was the average number, like what was the percentage, average winning, I guess. np dot average or np dot mean of all our winnings, even though it was just ever 1 or -1. On average, we lost that much each time. That's interesting to think about, even when we won. So like that's why the house wins always. We also now, because this is an array, we could do table stuff. We could graph it if we wanted to, make a histogram, like if it had multiple different values, because now an array could become a column of a table, right? It's not just one value anymore. So we can make a table, like here are all the outcomes. Start with an empty table, add a single column to it. That's kind of nice. Like that's my winnings. What is outcomes now? And now I've got a table with a label, and like it's got so many cool things. I can make graphs. I can be like, all right, outcomes. Oops. I hope I didn't mess with something here. Hopefully we're fine. Outcomes dot, we can like group it by the winnings now, because like it's either 1 or -1. That will be fine, right? It's fine with this, when it's a number like that. There's only a couple. I can group. Oh goodness, what just happened? Oh, I treated it like markdown. I did some weird key combinations. Like, all right, it counted the ones and -1s. Like you can tell it to do that now because it's a table. You can turn it into a table. That's useful. And after you group like that, you can make, even though these are numerical values, you can think of it as categorical things. You could do a bar chart on the winnings column. It's like, oh, it looks like you can kind of, now visually you can see how many more times you lost, right? And you can do this a bunch of times and see like how the graph changes. Like it was more interesting now to keep track of each individual outcome, and you can do that with an array. Like append the new value each time. You could have done this 1,000 times. It's as simple as changing that to 1,000, isn't it? That's kind of neat, right? Are there any questions about that entire process? You see the usefulness of it, I hope. That's kind of cool. Let's see what else do I want to do here. Oops, I accidentally closed my notes page. Give me a second. Well, we could also deal with, what was the other thing I promised to do? We can do coin flipping. It's like, all right, how many times was it heads? How many times was it tails? And we can keep track of each amount now. You kind of know how to do that with np.random.choice. Gets you most of the way there, but you could have done fancier things. Let me show that to you. So here, we know how to flip a bunch of coins with just np.random.choice. We still have coin. Let me bring that on down here. So remember that we've got our coin array still. It's just heads and tails, those two strings. And we can ask to flip a coin 42 times. We can ask to flip a coin 100 times, and we're going to get back an array of random values of that length, right? So cool. We could do something like this now, like flip 100 coins. Here are outcomes. This is what happened. We can count how many heads there were. We know how to do that, right? It's like we take our NP dot, like our value, we take our outcomes, and we count the non-zero elements after comparing it against, was it heads? Because that'll give you a bunch of trues and falses. You can count how many there were. NP dot count non-zero, because true is non-zero, false is 0, and apparently there were 46 heads. Remember that game we played there? And so you can keep track of the number of heads that way, num heads. But on average, it'll be around 50, right? Because we flipped 100 coins, and it's randomly, perfectly random. It's a fair coin. So that's num heads. And it'll be a different amount each time. So I run it again. Now it's 55, more heads. Cool. We can turn this into a function, like a function that flips 100 coins and counts how many heads there were. Why not? I'm going somewhere with this. This is interesting. I promise. So like, let's make a function called flip 100 coins and count heads. It'll take nothing. It just goes and does something for us. It doesn't need to take anything on. It just runs all these. Runs these lines, and it has to give the answer back though. So remember to indent, and like the answer that this gives back is the num heads value. So now I can call this function and always get back like this function. Every time I call it, flips 100 coins and counts the heads. Boop. One time, another time, another time. Is what I've done made has what I've done made sense so far? I made a function to do that. It's like, all right, flip 100 coins, count the heads. Cool. Because now I can do that 100 times, 1,000 times, couple thousand times, whatever you want. In fact, I'm going to do it a certain variable number of times. Like, how many times do I want to repeat this experiment? I'll call it num repetitions. Let's be like, computers are fast. Let's play this game 20,000 times. Why not? But you can change this to whatever you want. It's like now I can make a loop that goes num repetitions times by saying for I in np.a range num repetitions, right? Because if it was 100, it would go up to 100. Just like whatever was in that variable, it'll run this body that many times. So it's going to run it to 20,000 times right now. All right. So what do I want to do? I would like to do this 20,000 times. Give me 20,000 flippings of 100 coins and counting their heads. Okay, that's what I want. I can do that, and I can keep track of each outcome, each result from all the 20,000 or however many I put there times. I'll call it head counts. I'll start it off with an empty array so I can fill it up. Fill it up each time I do something. So each time, each of the 20,000 times, I'm going to run code. I'm going to run the lines in this body. I can get a single head count. Like my head count this time was a call to this function. Like it's going to flip 100 coins and count the heads. And I can add whatever that was to my running list of all the head counts I've ever received. There will be 20,000 elements in that array by the time I'm done. Does that make sense? It'll be interesting to see what happens, because large numbers do things that are cool. So I want to say like, I want to append, right? np.append to my head counts the new head count. And like that's set that back into head counts. So like that's going to extend it one by one each time. And if I run this, blink of an eye, I did it very quickly. I now have a head counts array. If I ask for its length, it legitimately is 20,000 elements long. Very large. If I asked for, hey, Jupyter, show me head counts, it's not even going to try. It'll just say ... but we got 20,000 elements. You see how they're kind of close to 50 a lot of the time, but just off by a little. Sometimes they're more, sometimes they're less. But you can now make a table of these. So that's kind of interesting. So let me show that to you. You can make a size 20,000 table, length 20,000 table, 20,000 rows. Why not? It's like that. Those are my results. So does it make sense what I've done so far, though? It's like I have flipped 100 coins and counted the heads. I've done that process 20,000 times. So really, if you think about how many coins I've flipped, it's 20,000 times 100. So that 2 million or something. So that's interesting in itself. But let's make a table of all this, like table.with columns. So let's make a column for like the number of heads, of course, which is just head counts. But we can also like do other things. We can be like, we can make a label for like which head like if you number each repetition, like repetition number 1, it was I rolled 40 or I flipped 47 heads. Repetition number 2, I flipped 44 heads. Repetition number 3, I flipped 51 heads. Like you can keep track of that. So like which repetition number was this? I think that's how you spell it. Which is just a range, right? np.arange starts at 1, goes up to num repetitions, whatever that was, plus 1, right? To make sure it does it right. And those are our 2 columns in our table, and I can call that results. Results. Something like that. And so there are 20,000 rows in this table. Repetition 1, we didn't have that many heads. Repetition 2, we had that many heads. But like that's an interesting table to look at now. And let us make a histogram, because it's going to look very pretty, I promise. So here, let's do results, because now it's a table, right? Let's make a histogram of the number of heads column. So really, I didn't really need the repetition number, but that's okay. And it's going to look like that, but you can change what the bins are. Be like, how many bins? You can give it like a number for how many bins you want. Like, make 50 bins, please. And it'll look like that. Or you could like make your own bins, because it looks like the values kind of are between like 30 and 70-ish. Like that's a good value. So maybe we can go by a good amount that I noticed before. Is like bins is np.arange. Let's go from like, I don't know, so that they're centered properly. You can go by like 0.5, so 29.5 all the way to 70.5, I guess, at the other end of that. 70 point, but really like 70.6 and go by 1 each time. That could work. That's kind of pretty. That's a graph shape that you will get very, very familiar with in this class, all right? So there's somewhere we're going with that. There's a reason I did this one, but that's a good one to think about. Are there any questions about how we got to this, though? It's like I flipped 100 coins 20,000 times, and I counted how many heads I ever got, and it looks like you can see that it's very, very unlikely. It never happened, right, that I got 30 heads. I never got 70 heads. But I did get this range. It's very unlikely to get these ones, but I got a few of those, like a decent amount, like almost like 65 or so heads. That happened once or something. I don't know. But usually, like the bulk of the work, it's like, because it's a fair coin, you're going to get around 50 heads. Like that's going to be the most numerous outcome. And things around those kind of like fall off in that kind of way, all right? So it's called a bell curve, if you've heard somebody say that before, or you've taken a statistics class. So yeah, that just happened out of that experiment that we did, okay? Are there any questions about any of that? So I think that's a good example to stop on for the day, because we're just about out of time. I like to go for an hour and a half if I can. That's going to lead us to like actual probability stuff, and then we can do cool things there. But I think that is a good place to end. You can also be like, what was the average number of heads? Like, what do we call it? Head counts? Head counts. What was np.average of those? Very, very close to 50. If you did 200,000, this would be like probably even closer, rounded up to the like close to like to 6 more decimal places or something. But like that's cool to think about, right? And so yeah, I think that's a good place to end for the day. Are there any last questions about anything we talked about before I let you work? All right, I think that's all that I wanted to say. So the rest of the time is all yours to work and ask questions.